Hello. In this video, I'm going to take you through one of my fall 2022 practicum projects. I've been beguiled for many years by the desert southwest of the United States. I have a lot of exploring that I'd like to do in the desert southwest. Thus, I'm contemplating establishing a home base in the southwestern US. I'm considering Tucson, Arizona. Tucson is a nice medium-sized town. It's not huge, it's not tiny, and it has a college town vibe to it as it is the home of a major university, the University of Arizona. I thought it would be wise to apply my data analytics skills to the real estate marketplace so I can calculate the fair market value of a property in which I may be interested. In this project, I developed several machine learning models to predict residential real estate prices in Tucson. Here is our agenda for today. First, I'm going to demonstrate how I obtained the data used to train the models. We will leisurely peruse the data. We'll create a linear regression tree and use some techniques to sort out which variables are the important ones for the prediction we're trying to make. We'll use the ensemble learning features of the carrot package in R to generate several different models. Then we'll choose the best model and use it to make a value prediction on a hypothetical property. My primary data source was the Pima County Tax Assessor's Office. The tax assessor's public records contain many details about the homes in Pima County. The features that I've chosen are the current full cash value, which I understand is the tax assessor's calculation of market value. Class, this has to do with the design, workmanship, and materials. That's the description from the tax assessor. Quality, to stratify homes within the same class. District, this is a categorical variable to account for differences in neighborhoods. Construction year, livable square footage, the number of stories, the number of rooms, the number of garage parking spaces. You know how more expensive homes have 3 or 4 car garages. The number of bathroom fixtures. This was a little bit of an odd one, but I thought the more expensive a home is, the more bathrooms it ought to have, and thus more bathroom fixtures it will have. Whether or not the home has a pool and land area. Now, I'm not interested in analyzing all the values for all of Pima County. In fact, for that matter, I'm not interested in all the parcels in Tucson. I'm going to add an element of original research to my project. Tucson has a network of very nice paved trails suitable for walking, running, biking, rollerblading, walking your dog, leisurely walking, whatever. These are mostly along ephemeral streams, drainage ditches in other words, but they're really nice. As a calorically gifted person, I'd like to live near these trails, so I'm limiting my project to parcels within 1 mile of these trails. I feel these trails are a nice amenity to have access to. Therefore, I suspect that homes closer to the trails may be worth a little bit more. So I'm going to introduce a variable that I calculated myself. For each parcel, I've calculated the distance in feet from the parcel centroid to the nearest trail. And I'm going to add that number, the number of feet, to my list of features in my machine learning models. Let's examine the data using a correlation matrix. Recall that in a correlation matrix, the numbers range from -1 to +1. Numbers close to -1 mean that there is a negative relationship between those two variables, and numbers close to +1 means there's a positive correlation. In this diagram, the top row, cash value, is the variable we're trying to predict. So let's pay special attention to variables that seem to be highly correlated with cash value. We have class, bathroom fixtures, and square feet. And it makes sense. Those would seem to be correlated with cash value. When we're looking at the correlation matrix, we also have to pay attention to any independent variables that may be strongly correlated. If we see very strongly correlated independent variables, there may be some redundancy among the variables we chose. And I don't see anything particularly bad here. Perhaps square foot is strongly correlated with bath fixtures, but I'm going to leave those variables for now, and we'll see what the models come up with. Let's start our machine learning adventure by using a regression tree. A regression tree is a relatively simple form of machine learning, yet I think it will yield some useful information, and besides, it's kind of fun. Let me demonstrate how to use the regression tree. Each node on the tree is a simple yes or no question, and you follow the lines based on your answer. So, let me price a hypothetical house using the regression tree. We start at the top. Is the home less than 2,347 square feet? I don't need a lot of space, so I'm going to say yes, it's less than that amount. So I get to this node. Is the square foot less than 1464? Well, for now I want a little more than 1464, so I'm going to say no, it's not less. Is the class less than 4? I don't need anything posh. I'm going to say yes, the class is less than 4. Now here it asks if the home is in one of these districts. Well, for now I'll say yes. And so now I know, based on these selections, I can expect to pay about $200,000 for a home in Tucson. I notice that had I answered this last question differently, the home would have cost more, so I guess there's something undesirable about those districts. Now, let's take a little inventory here. We fed the regression tree 11 features and asked it to find one dependent variable, the price. But how many of those features did it actually use? Let's count. Well, it used the square feet, it used the district, it used the class, and over here it used the land square feet. Only 4 of the 11 features it used. So before we proceed to the more complex machine learning algorithms, we need to sort out which variables are important and which variables aren't. When we looked at the regression tree, we started to suspect that perhaps not all of the variables that I selected are required to generate a good calculation of value. So before we proceed to the more complex machine learning methods, let's do a process called feature selection to sort out which variables are important and perhaps which are not. The metric that I choose to use to evaluate the efficacy of my models is R squared. R squared refers to how much of the price is explained by the input variables, the features. And using 16 variables, we come up with an R² of 0.94. And I'm quite proud of that. I'm quite happy with that. With a mean absolute error of 14,257. That means the model acknowledges that it may be off by $14,257. Now, if we go up to 30 variables, we do indeed get a slightly higher R², which is good, and a lower mean absolute error, which is good as well. However, we get into something that in the machine learning world we call the curse of dimensionality. When we start adding variables, it increases geometrically the amount of work that the computer has to do. So the difference between 16 and 30 variables is a lot of extra work for the computer without receiving a lot of value in return. So I'm going to stop the analysis at 16 variables. Perhaps in the future, if I'm doing this, if I'm actually looking at properties, or perhaps in the future, when I have access to more powerful hardware, well then I'll do the full 30 variables. But for now, we're just going to stick to 16. Okay, so we've chosen to just use the 16 most important variables. What are those variables? Here are the 16 most important variables. Now, recall that district was a categorical variable, a text variable. Machine learning algorithms cannot cope with text. Everything has to be numeric. So, for each district, we needed to create what's called a one-hot variable, which is simply a Boolean 0 or 1 value to indicate whether the property is in this district. So that's why our number of variables has ballooned to 30. So here are the 16 most important variables. Year, we see a number of districts. Square foot, that makes sense. Quality, class, land square foot, and distance from trail. That's the one that I created, and it made the top 16. Garage capacity was at the very end of the top 16. So what didn't make the cut? Stories, rooms, several of the districts, whether or not it has a pool, because that wasn't important. Bath fixtures, perhaps square footage has collinearity with bath fixtures, and that's why it threw it out. So now we can proceed to running the machine learning with these 16 top variables. Here's what I came up with. I asked Carrot to generate for me 5 different models using 5 different machine learning methods. In each graph, each dot represents a member of the test data set. Each dot's position along the x-axis refers to the tax assessor's value, and its position along the y-axis refers to the value that the model calculated for the property. A good model will have the dots clustered closely to the regression line. The closer the dots are to the line, the less error in the model. So, let's see who's the winner here. The winner is the stochastic gradient boosting model with an R² of 0.95. The runner-up is the extreme gradient boosting linear model with an R² of 0.94. And the bronze medal goes to the extreme gradient boosting tree model. All of those were very good. Trailing is the linear regression model. That's a simpler model. I guess it couldn't compete with these more complex models. Now let's turn our attention toward using these models to make a prediction. Let's review briefly what we just did. We created 5 machine learning models for our project, and we selected what we feel is the best one. Now, what do we get in exchange for our effort thus far? Do we get any adulation? Do we get any approbation? No, we don't. But what we do get is we get a model that we can use to calculate the fair market value of a property in which we may be interested. In this series of variables, I have supplied values for each of the features that go into the machine learning model. All of these values are hypothetical, but feasible. Then, I'm using the predict function to use the GBM model on these hypothetical features that I just created. Let's run the model and see what happens. Okay, it's coming up with a value of about $249,000 for this hypothetical property. Now, the other machine learning models are available and we can use them as well. Let's do that. For the XGB linear and XGB tree models, they calculated a rather different value than the GBM model did. This brings us to another question. What features are most important, according to the machine learning model, for making these calculations? Let's look at that now. Let's look at this graph together. For each feature, there are 3 bars, each bar corresponding to one of our top 3 models. We see here that the different models put different levels of importance on features, but they generally agree that square footage is the most important element of value, followed by class. Recall that class has to do with workmanship and quality of materials, and land area. Some districts have a small effect on value, while others have practically no effect on value. Note that the variable that I created, distance from the trail, contributes something to the model, but its importance is very minor. Now, the importance of this graph is so that if a salesperson tells me that a home is worth more because of, say, its proximity to the trails, or whether it has a pool, we know to investigate the veracity of those claims. Wasn't that fun? Thank you for joining me on my machine learning adventure. If you'll excuse me, I have a lot of exploring to catch up on. I'll see you out on the trail. So long.